Hello friends, welcome to lecture number 3 of WAVE chapter. In previous class what we discussed? We completed the different terms used in wave as well as the very important wave velocity, which is also called as phase velocity. And also you understood that wave velocity is different from particle velocity because wave means oscillation plus propagation. So oscillation velocity, that is particle velocity, but propagation velocity, that is wave velocity. And also we derived the expression for wave velocity, transverse wave velocity, and then longitudinal wave velocity. So finally, what expression we derived in the previous class? V is equal to the longitudinal wave velocity. V is equal to B by rho root over. We ended the class here. B is the bulk modulus. Rho is the density of the medium. This is the velocity of a longitudinal wave passes through a medium. But what happens to the velocity of a longitudinal wave means sound wave. Take the example sound wave. What happens to the velocity of a sound wave in air medium? What will be the expression of it? That one today we will discuss. What is the expression of a velocity of sound in air medium? That one we will discuss. We'll derive means actually one great scientist has given one formula here, already derived the formula, already gave the idea about the velocity of a sound in air medium. Who is the great man who always gives formula in all chapters of physics? Who is that great man? Newton. Obviously Newton. So now the question is coming to your mind. So Newton also gave the formula in wave chapter? Yes. Newton, the great man, initiated all the chapters of physics, given formula in all chapters of physics. Also not left to wave chapter. So now today we'll discuss the very important. This also comes as one derivation also in your exams, that is Newton's formula. So let's discuss today Newton's formula. So what actually Newton told? What the great man told about the velocity of sound in air medium? You will be astonished. This great man relate wave chapter with thermodynamics chapter. Wave with thermodynamics. Then the question is coming to your mind, sir, how? Sound propagate in a medium, sound propagate in air, that's a wave, longitudinal wave. How it is related to thermodynamics? According to Newton, propagation of a sound in air is an isothermal process, which you may not thought about this. The propagation of a sound in air, Newton told, is a thermodynamic process. That to which process? Isothermal process. You see how this great man relate propagation of sound with thermodynamic process. The question is coming to your mind, then if isothermal process, then temperature should remain constant. Then how Newton explained it? How Newton explained that temperature remains constant? Newton also explained it. How? How Newton explained the propagation of sound as isothermal, how temperature remains constant? Newton told, during compression, you know sound propagate forming compression under air fractions, longitudinal wave. During compression, heat is released to the surrounding, and during rarefaction, heat is absorbed from the surrounding. In this way, temperature is maintained as constant. Got it? How Newton beautifully explained? Newton told, again I repeat, During compression, heat is released to the surrounding. During rarefaction, heat is absorbed from the surrounding. In this way, temperature is maintained as constant. So no rise or fall of temperature. Temperature is maintained as constant. As temperature constant, then it is an isothermal process. Newton told like this. According to Newton, propagation of sound in air is an isothermal process. Temperature is maintained constant like this. Okay, if it is isothermal process, it must obey the equation of state. What's the equation of state of isothermal process? You have read in thermodynamics. Okay, equation of state, the answer is coming to your mind. Good. Sir, PV is equal to constant. PV is equal to K. This is the equation of state of isothermal process. Now let's modify this expression, original expression, to Newton's formula. Okay, so now let's convert this expression to Newton's formula from the equation of state PV is equal to K. Then differentiate both sides with respect to volume. Differentiate both sides with respect to volume. So here pressure is a variable, volume is also variable, as both quantities variable. So what we'll do? So now we have to use which rule in this differentiation? As both variable, we cannot take any quantity to outside of this differentiation. What do you have to do? Product rule? That's right. We'll use product rule. So first one is taken as constant, second derivative, then the second one, then the first derivative. First one constant, second derivative, then second constant, then first derivative. Then it's a constant, its derivative is 0. Then it's coming dv by dv is 1. So this is p only. Then p plus this is v, dp by dv is equal to 0. So now keep the p here. So this is minus v dp by dv. So implies that p is equal to minus dp dv by v. I hope it's mathematical correct. I just bring this v to this side. If I multiply, then it will go to the numerator. It's right. So this formula, have you seen this formula anywhere in previous chapters? Just recall where you have seen this formula. Solid chapter? Yes, in solid chapter you have seen this formula. Pressure divided by, this is what? Volumetric strain. Volume strain. So pressure by volume strain. What is this? Means stress by strain. So this is nothing but bulk modulus. This is the bulk modulus. Minus sign is included there in the bulk modulus because pressure volume are inversely related. So here P is equal to B. So what you got? What you got here now? Bulk modulus is equal to pressure. According to Newton, bulk modulus is equal to pressure. If bulk modulus is equal to pressure, then what is your final expression? V is equal to, so B in place of B you put now P by root over. Got it? This is called as Newton's formula. This is the Newton's formula for velocity of a sound in air medium. Got it? But you will accept it. You will believe it. Yes, you have to believe it. But only under a condition. What is the condition? Experimentally also it should be correct. We'll check this formula whether applicable or true experimentally or not. Theoretically we derived. When some scientist derived theoretically, also we have to check it practically whether it happens or not. Okay, so we'll check it practically, then we'll accept the formula of Newton. Clear? So now let's check practically what we'll accept here practically. Now let's take it. At NTP, you know at NTP now. Let's find the expression of the velocity at NTP. What happens? So here at NTP pressure is how much? This is 1 atm at NTP. Okay. Then density of air, this is 1.29 kg per meter cube. This is the standard value. Density of air 1.29 kg per meter cube. This is 1 atm. You put the values here, P by rho root over, then you put the values. So 180 means how much Pascal? 1.013 10 to the power 5 Newton per meter square. Then this is 1.29 root over. Do the calculation. How much will get? 280 meter per second. If you will do the calculation. If you don't believe me, then you use the calculator and do it. Okay. So you will get nearly 280 meter per second. The question is coming to your mind. What is the velocity of sound at NTP, sir? Actually, what is the velocity of sound? Practically. Experimentally, the velocity of sound in air at NTP is 331 meter per second. Nearly 331 meter per second. If it is nearly 331 meter per second, but this is the experimental value. But Newton's theoretical, from the theoretical formula, when you calculate, then according to Newton's formula, the velocity of sound is coming to 80 meter per second. We'll accept it. Let's check the percentage of error first. How much percentage of error Newton commit? Okay. Now let's calculate the percentage of error. Percentage of error, how will you calculate? Change in value by original value into 100. Let's do change in value. 331 minus 280 by original value is 331. Then into 100. You do. Into 100. Change in value by original value into 100. You do the calculation and see how much it is coming. It is coming nearly 15% or 16% like this. 15 point something, so nearly 15% error is coming. We'll accept Newton. 15% error. In the practical lab, when you do 5% error, more than 5% error, then the teachers are getting angry on you, not giving mark in the practical examination. More than 5% error is not accepted. We'll accept Newton's formula, which is with error of more than 15%. No. So Newton's formula is now proved here as wrong. Then the question is coming to your mind, sir, then what Newton did? But the great man gives us the path. The great man gave the path here to find the expression of a velocity of sound. May be wrong, formula may be wrong, but gave the path, gave the idea that relate wave with thermodynamics. It's a great thing. Okay? But then who corrected this formula of Newton? Who corrected this formula? Another scientist came, Laplace. Laplace came to correct Newton's formula. Now let's discuss Laplace's correction. Let's come to Laplace's correction now. What happens in Laplace's correction? So what Laplace is told, what changes Laplace did, and what Laplace is told actually in Newton's formula. Laplace is told velocity of sound in air medium is not isothermal. Not isothermal. Newton told isothermal, but Laplace is telling not isothermal. So why not isothermal? If not isothermal, then Laplace has to explain why it is not isothermal. Laplace has to explain. Then what Laplace is told? Laplace is told it is not isothermal. Then what is it? It is adiabatic. According to Laplace, propagation of a sound in air medium is an adiabatic process. Adiabatic process. If adiabatic process, there should be no exchange of heat, pressure change, volume change, temperature change, but there should be no exchange of heat. Then how Laplace has explained this one? Yes, Laplace has explained. Laplace has told 2 points. First point, air is a bad conductor of heat. Laplace has told air is a bad conductor of heat. That I know, you know, everybody knows air is a bad conductor of heat. Yes, air is a bad conductor of heat. Laplace has told when air is a bad conductor of heat, how the question comes, exchange of heat. Yes, this may be true. Because air is a bad conductor of heat, then how the question comes, that heat release, heat absorb, how this question is coming to Newton's mind. Okay, then what the second point told? Second point told, Laplace also told sound travels very fast. 331 meters per second is not a small speed. Sound travels very fast. When sound travels at such a faster rate, when it gets time to exchange of heat, it's a sudden process. But isothermal is a very slow process. But adiabatic is a sudden process. Laplace is told propagation of sound is a sudden process. Sudden happens this one. The very fast happens. There is hardly it gets time for exchange of heat. So 2 points Laplace has now told here. First point, air is a bad conductor of heat. No question of exchange of heat. Second point, sound travels so fast it hardly gets time for exchange of heat. So propagation of sound in air medium is an adiabatic process. This seems to be correct. But will not believe. This seems to be correct. Laplace seems to be correct, but will not believe. We'll see what formula Laplace gave. Then we'll check it experimentally. After that we'll believe. Okay. So now let's see. If it is adiabatic process, then what is the equation of state? Again start from the equation of state. PV to the power gamma is equal to K. So now differentiate it with respect to volume. So this side also with respect to volume K. So this is coming P V to the power gamma differentiation. Then V to the power gamma dp by dv. Constant differentiation is 0. I use which rule here? Same as the previous product rule. Then P V to the power gamma differentiation gamma V to the power gamma minus 1. X to the power n differentiation formula n x to the power n minus 1. Then V to the power gamma dp by dv is equal to 0. You take V to the power gamma here, V to the power gamma here, take V to the power gamma common. What remain here? Gamma p, then V to the power minus 1 I take to this side. V to the power gamma is taken common, so dp by dv is equal to 0. So V to the power gamma comes to this side and vanish. How much remain here? Gamma p by v plus dp by dv is equal to 0. Okay, now let's see. Implies that gamma p by v is equal to minus dp by dv. So gamma p is equal to minus dp by dv into v. So implies that gamma p is equal to minus dp dv by v. Hope you understood the mathematics what I did step by step. You can see it again. Okay. So this one already you know the formula for which quantity. This is the formula of bulk modulus. Again, so what is the expression now? V is equal to B by rho root over, in place of B I write gamma P by rho root over. So this is Laplace's correction. Laplace's correction. Only in the correction what happened? What changes is done in the correction? Only the gamma includes here. What is this gamma? You have remembered Cp by Cv, gamma. Okay. So, but we will not believe it. What we'll do? We'll check it also experimentally, this formula. Let's check what happens at NTP. at NTP. At NTP now, see here again, V is equal to, we'll put the formula here direct, gamma P by rho root over. So gamma you separate, P by rho root over you separate, because already you have calculated P by rho root over. Newton has done the calculation of P by rho root over. So gamma root over, but gamma is how much for air? Gamma, you know, you have calculated in kinetic theory of gases. For monoatomic, diatomic, triatomic, just recall. If you forget, see your copy, okay? See your copy and find the value for gamma. But which gamma you will take, the question is coming to your mind. So we'll take mono, or we'll take for dia, or we'll take for tri. We'll take for dia. Why dia? Because in gas, maximum content is what? Nitrogen. In atmosphere, maximum content is what? Nitrogen or then oxygen. Okay, and both are diatomic. Nitrogen, oxygen, they are diatomic. As maximum content diatomic, so let's take this gamma for diatomic gas. What is the value for diatomic gas? How much? You have remembered? Okay, 1.4. 1.4 is the value for diatomic. Then P by rho root over is 280. If you multiply, you do the calculation using calculator. If you don't believe me, okay, 331.3 meter per second it is coming. 331.3 meter per second. But experimentally, what is the value I told you? 331. This 331.3. Now the experimental value is in close agreement with the theoretical value. So Laplace's seems to be correct. Not seems to be, Laplace's is correct. Okay. So in this way, Laplace's correct Newton's formula, which comes as a small derivation, 3 marks derivation in your examinations. So finally, you got the expression of velocity of a sound in air medium. Then what is your expression? Gamma P by rho root over. So with this formula, now we'll proceed again. We'll discuss. So the velocity of sound in air medium actually depends on which quantities. Now let's discuss. Velocity of sound in air medium depends on which quantities. Now let's discuss that one. Depends on which quantity. So this expression over. Your final expression in your hand is what? Remember now, V is equal to gamma P by rho root over. Remember the formula, then it will be easy for you to solve the numericals. Okay. Then using this formula, we will proceed further. How velocity of sound depends on which quantities. First, let's check. Number 1, pressure. How velocity of sound in air medium depends on pressure. Let's check pressure. What is the expression? You tell me, you think the answer, because you have the formula now in front of you. So how velocity of sound depends on pressure? Okay, it's very clear. Velocity of sound is directly proportional to pressure root over. V directly proportional to root under pressure. Then we can write the formula. V1 by V2 is equal to P1 by P2 root over. Got it? You should remember this formula to solve the numericals. Okay? You also, now I think already remember this formula. Okay. So this is a biggest mistake. If you are writing now this one, so this is a biggest mistake. This is completely wrong. Completely wrong. You are getting astonished. Sir, you wrote the formula, now you are telling it's wrong. Yes. Dear students, one thing always keep in mind. When you are going to find the relation between two quantities, just have a look on the other quantities in the expression, whether they are affecting their relationship or not. Got my point? Not only here, throughout the physics you apply this concept. When you are going to find the relationship between two quantities, velocity and pressure, some other quantities are also there in the expression. You check whether they are silent or they are violent. Okay, so they are silent or they are violent. They are not silent. You see, gamma is silent, gamma is constant. But density, that is not silent, that affects the relationship. So you cannot say the relationship between V and P only. Got my point? So this is the wrong thinking. Don't do like this. Don't do like this. Then the question coming to your mind, sir, what happened? Then how velocity of sound in air is affected by pressure? How it depends on pressure? Now you see, when pressure increases, when you increase the pressure of air, what happens to volume? Volume decreases or not? When pressure increases, volume decreases. When pressure increases, so volume decreases. If volume decreases, what happens to density? Density also increases. Got my point? If pressure increases 2 times, volume decreases 2 times. Density increases 2 times, so pressure increases 2 times, density increases 2 times. So 2 cancel. 2 cancel. That means density increases proportionally with pressure. If pressure increases 2 times, density increases 2 times. So, what is your conclusion? Velocity of sound in air medium is independent of pressure. Got it? Velocity of sound in air medium, this is independent. This is independent of pressure. Remember this one. Velocity of sound in air medium is independent of pressure. Okay, don't do the mistake P1 by P2 is equal to P1 by P2 root over. Because when pressure increases, then density also increases proportionally. Then come to the next point. How velocity of sound then depends on what? Temperature. Let's check how velocity of sound depends on temperature. How it depends on temperature? What answer is coming to your mind? Now you think about it. Is there any quantity like temperature here? Is there any quantity? Temperature in the velocity of sound expression? There is no such quantity like temperature. If there is no quantity like temperature, then what will tell? So the answer will come to your mind that velocity is independent of temperature. This generally this answer comes to the mind of the students. As there is no temperature in the expression of a velocity of sound. So we'll write velocity is independent of temperature. No. If temperature changes, now some change also happens here. Okay, now see what happens. Don't tell wrongly that velocity of sound is independent of temperature. No. You check in the expression, temperature is hidden. Temperature is hidden there. Okay, so V is equal to gamma P by rho root over. Then what you do? Gamma P. So in place of rho, you put mass by volume. Density, mass by volume. But I have taken molar mass. Okay, for 1 mole I wrote this expression. So I take molar mass here. So gamma PV by m root over. So it is coming what? So it's coming gamma. Then in place of PV, ideal gas equation. Okay, PV is equal to nRT. But I will take RT because I am writing a molar mass for 1 mole. So this is velocity of sound. This is one formula. This is another formula, also one more modified formula. Velocity of sound in terms of temperature. Now you tell me, velocity of sound depends on temperature or not? Okay. So here you have to check other quantities are constant or not. So gamma constant, R constant. Here the molar mass constant means for a particular gas we have to check. For a particular gas, velocity of sound. Okay, for a particular gas, velocity of sound, how depends on temperature? Velocity of sound is directly proportional to temperature. Directly proportional to square root of temperature. Square root of absolute temperature, not only temperature. Okay, you correct the sentence properly, tell the sentence properly. Velocity of sound for a particular gas is directly proportional to square root of absolute temperature. Got it? Absolute temperature. So V is proportional to T root over. So V1 by V2 is equal to T1 by T2 whole root over. This is the dependence of velocity of sound with temperature. But we'll again modify this formula little more. Let's see what modification I am doing here. You see, so V1 by V2 is equal to T1 by T2 root over. So V1, so let's check at 0 degree Celsius. 1 I am taking 0 degree Celsius, 2 I am taking T degree Celsius. Okay. So 0, 1 means I am taking 0 degree Celsius, 2 means I am taking T degree Celsius. So this T1 will be 0 degree Celsius. So this will be how much? 0 degree Celsius, but I have to convert that into what? Kelvin. Because that is absolute temperature. Keep in mind, that's absolute temperature. This is T degree Celsius plus 273. It's a half power. Square root means half power. So implies that Vt by V0. So we have to change this 273 by 273. I change it. This is half power. Okay, this is half power. Correct? Just I change the numerator to denominator, denominator to numerator. Right? Then Vt by V0 is equal to 273 by 271 plus T by 273. It's a half power. So how much is coming? Vt by V0 1 plus T by, how I will expand it? The half power, how I will expand? I have to use which theorem? Always what we do in physics? Binomial theorem. Okay, we use binomial theorem and we neglect the higher power terms because the second term is very less. So how we use generally the binomial theorem? Just multiply the power in the second term. Just multiply the power in the second term. Now the binomial theorem is used here. You can write here, using binomial theorem and neglecting higher power terms. Condition is second term is negligible. Okay, so half power you multiply here, then binomial theorem is automatically used. If you use according to your mathematics point of view, then also you get the same answer. So 1 plus T by, you multiply it, 6, 4, 5. Hope I am correct. So Vt by V0. So finally Vt is equal to V0 whole into 1 plus T by 5, 4, 6. This is your formula of velocity of a sound at any temperature. You can remember this formula to find velocity of sound at any temperature. Okay, so this is the expression of velocity of sound. How velocity of sound depends on temperature. But let's again find the change in velocity of sound. What I am doing, you see here, Vt is equal to, I just multiply inside the bracket, V0 divided by V0 T by 5, 4, 6. So it is coming Vt minus V0 is equal to V0 T by 5, 4, 6. So Vt minus V0 is what? This is the change in velocity of sound. Then V0 is the standard value. At 0 degree Celsius, velocity of sound is 332. 332 into T by 546. By 546. So it is coming 0.61 into t. Okay, 0.61 into t. 0.6 or 0.61 into t. But if you take, if t is equal to 1 degree Celsius, then del V is coming 0.61 meter per second or 61 centimeter per second. What you understood from this conclusion? You see the mathematics again. Okay, so see the mathematics again, and what you understood from this? Change in velocity is coming 0.61 meter per second. What is your concluding line? Concluding line. That means for every 1 degree Celsius, for every 1 degree Celsius rise in temperature, for every 1 degree Celsius rise in temperature, velocity of sound raises by, velocity of sound is raised by 0.61 meter per second. When temperature increases by 1 degree, velocity of sound increases by 0.61 meter per second or 0.6 meter per second. Remember this line. Okay. For every 1 degree Celsius rise in temperature, velocity of sound is raised by 0.61 meter per second. So this is the dependence of velocity on temperature. Next, which one it will say how the velocity of sound depends on density. Now let's check. Let's check how it depends on density, because we see one density symbol is there in this expression. So we must discuss how velocity of sound depends on density. Now let's check how this velocity of sound depends on density. Number 3, density. So how it depends on density? So V is equal to gamma p by root over, p by rho root over. Okay, what happened? So if we see the relation between velocity and density, we have to keep pressure constant. Otherwise pressure will affect density. We have to keep pressure constant. Okay, so at constant pressure, we have to keep pressure constant. The question is coming to your mind, sir, can we keep pressure constant for different density? Yes. Now in air, everywhere the pressure is 1 atm, but density is different for different gases. For example, you see oxygen density is 16 times greater than hydrogen density, but pressure is 1 atm. Pressure constant 1 atm everywhere, but density varies from gas to gas. Okay, but are you thinking the first case what I told you while discussing the velocity with the pressure dependence? Okay, but there we cannot keep density constant. Once you increase the pressure means density automatically increases. We cannot keep density constant if we increase the pressure. If we increase the pressure, we cannot keep density constant. Remember. But in this case, why I am telling? Because everywhere now pressure is constant. In atmospheric pressure everywhere. But density varies from gas to gas. Density varies from gas to gas at constant pressure everywhere. Okay. So what happens? How this velocity depends on density? Depends on density like this. Velocity is directly proportional or inversely proportional? Inversely proportional to square root of density. More is the density, less is the velocity of a sound. Okay. One question you can do, if possible, you write one question here. Density of oxygen is 16 times greater than hydrogen. Find the ratio of velocity of a sound in oxygen to hydrogen. I repeat this question. You note down. Density of oxygen is 16 times density of hydrogen. Find the ratio of velocity of sound in oxygen to hydrogen. Pause the video here, do the calculation, then after that you play the video. Okay? Pause it fast, then you see what I am writing. Okay? Hope you got the right answer. So what will do? Velocity of oxygen by velocity of hydrogen, I am writing the formula here as V inverse proportional to rho. So V1 by V2 is equal to rho 2 by rho 1 root over. So this is oxygen, this is hydrogen. 1 I am taking oxygen, 2 I am taking hydrogen. So this is density hydrogen divided by density oxygen. Okay. So hydrogen is 1, oxygen is 16 times. So it's coming 1 by 4. So your answer is coming VH is equal to, or VH, this was the question to find the ratio. So VO, oxygen to hydrogen, is equal to 1:4. The ratio of velocity of sound from oxygen to hydrogen is equal to 1:4. It can be asked as a question in exams. This is the dependence of velocity of sound with density. Now let's discuss how this velocity of sound depends on humidity. Humidity has any role in velocity of sound? Yes. Humid air. When the air becomes humid, means moisture present in air. Okay. When air becomes humid, means moisture present in air. When moisture present, then what happens? Is there any quantity which is affected by this? When moisture present in air? Yes. Which quantity? Density of air. When moisture present in air, density of air gets affected. How affected? Humidity increases. When humidity increases, what happens to density of air? What question is coming to your mind? In air, now water vapor enter. Water vapor enter. When water vapor enter, what happens to density of air? It increases. It's wrong. This type of wrong thinking sometimes comes to the mind of the students. So when humidity increases, water vapor enters, so density increases. No, it's wrong. Density not increase, rather density decrease. Why? You are getting astonished. Sir, density decreases when air becomes humid. Yes. How? Because when water vapor enters in air, it takes more space. Water vapor takes more space. Volume increases. Water vapor needs more space, takes more space. When volume becomes more, what happens to density? Density is less. Okay. So when water vapor enters in air, it takes more volume. So when volume is more, then density decreases. So if density decreases, what happens to velocity of sound? Increases. So velocity of sound is more in humid air. More is the humidity, more is the velocity of sound. Got it? How velocity of sound is affected by humidity? Then let's discuss. Any other quantities there which affect the velocity of sound? Yes. Another quantity is still there. What is that quantity? The quantity which affect the velocity of sound is air. Air blow, or that we say as, it's better, wind. Wind affect the velocity of sound. This affect? Yes. You are the sufferer. Many times you have suffered due to this wind. You are unable to pass the sound to your friend, to your brothers, to your sisters due to this wind. Where? Day-to-day life, you have already came across about this type of activities. But where? Okay, now you do the experiment. Take one table fan. You sit in front of the table fan. Make your brother or sister or friend to sit at the back of the table fan. Okay, so this is the table fan. This is the table fan. You stand in front of the table fan. Okay, you stand now in front of the table fan and speak something. Then here is your brother or sister is standing at the back of the table fan and he want to listen your sound. Sound he wants to listen. He is the listener. You are the speaker and this is the table fan. Okay, this is the table fan. When table fan switch is off, no problem. You will speak. Your brother or sister will listen. But you switch on this table fan. You on the table fan and now speak. When you do the table fan on, then what happens? What you speak, your friend or brother or sister, your friend is unable to listen clearly. Why? Because wind affects. Now wind blow like this. Wind blow like this and sound travels like this. Wind affect the velocity of sound. Got it? So you must have come across this type of situation, but you are unknown about this fact actually, how this wind affect the velocity of sound. How actually it affects it? You see, this is the velocity of sound. This is the wind blow. I am just taking the general case. Suppose an angle. Now wind blow, make an angle theta. This wind velocity can be resolved into two components. Here W cos theta. Here W sin theta. It has no role. This component has no role, but this component affects the velocity. What is the effective velocity of now sound? V plus W cos theta. Got it? This is the effective velocity of a sound. But what happens when theta is equal to 0? Then Vf is equal to V plus W. But when theta is equal to 180, then Vf is equal to V minus W. What happens in fan? What happens in fan? Okay. So when you speak in front of the fan, then the velocity of sound and the wind velocity are opposite to each other. But you rotate the fan towards the listener. Rotate the fan towards the listener, then it will be easy. Then it will be V plus W. So that means when both are in same direction, then wind helps the velocity of sound. But when they are in opposite direction, then wind opposes the velocity of sound, V minus W. So we discussed how Newton gave the formula, Laplaces corrected it, and then on what different factors velocity of sound depends. Thank you.